I appreciate it. I'm really happy to give the talk to the Society, having just recently joined. So this is kind of an interesting story. You may have heard about it last year. There was all this stuff in the news about the world's largest single volcano, in quotes you see up there. And it was really quite an interesting ride, so to speak, because it was a bit of science that I thought really wasn't all that important. But it had this little hook to it, largest volcano in the world. And suddenly everybody picked up on it, and it went viral all over the world. And it got a lot of attention, which is good. Although, honestly, that and a couple of bucks will get you a cup of coffee at Starbucks. But it has there's an interesting story here, an interesting bit of science, and also some interesting background, and I thought I would share it with you. And by the way, this is a neat graphic, but it has absolutely nothing to do with my talk. This is from the Discovery Channel program on the Yellowstone supervolcano, but that's the best thing I could find. So this is a story about hard work and a lucky break. I've been working on this for 20 years. Lucky break because last year, actually it was almost like in a fit. I had got a paper published in a journal called Nature Geoscience, which has a very broad readership. And in order to get that, well, it had been rejected 4 different times. Twice by another journal, and then twice by this journal. And finally I was at the point where the editor said, "It's a big volcano, so what?" And it's like, it's the biggest volcano I know of. And that became the hook. So that became what we publicized. And like I say, it wasn't even the basis of what we were doing out there research-wise. It was just one of those things. I thought it was an interesting fact. But anyway, it's also a tale about a name and institutional pride. So 20 years ago, we went out to study this mountain range. It's called Shatsky Rise. I'll show it to you here shortly. And it has these mountains in it. And well, it's kind of like going to the Himalayas, and you could say, well, there's that one on the right and that one on the left. And so we gave them names. And so I was at Texas A&M at the time, and it was my cruise, so I said, well, we're naming the biggest one Tamu, after Texas A&M. There's another one that we call Ori, after Ocean Research Institute, University of Tokyo, a colleague who was there. Another one named Shershoff, after the P.P. Shershoff Institute of Oceanology, but that was the smallest one. Tamu was the biggest one. So 20 years later, Tamu gets to have the biggest volcano in the world named after him. Also, this story highlights the difficulty of ocean exploration. It's all over the news right now. They want somebody to find an airplane maybe in the middle of the ocean. They're not going to be able to do it. You just can't do it physically. And the ocean is a very large place. It's very hard to explore. For years, we hid our nuclear weapons in submarines under the ocean. We probably still do. It is hard to find things under the ocean. A lot of people ask, well, why did we just discover it? It's because it took years and years to get the right kind of equipment out there to collect the right kind of data. Stuff that most of you guys who work in industry do all the time, by the way. All right, so one of the real questions is, the ocean basins are littered with thousands of seamounts, which are undersea volcanoes. Most of them are inactive, and as you look at the seafloor here, and I'm sorry I forgot my laser printer, so I have to drag around the cursor here, but there's the Hawaiian Emperor chain, there's a bunch of seamounts over in there, there's a bunch over in here, here's some in the Atlantic. They're all over the place. It's been estimated maybe 100,000 of them out there. So how the heck did they get out there? Well, that's a question that we'd really like to know as geologists, because the stuff that they form from, the magma, has to come from the Earth's mantle somehow. So it has to represent a flux from the Earth's interior to the exterior. And what are those big things out there? There's a big volcano. Cursor went away. There it is. So there's a big one. That's Hawaii. And there's the Hawaiian Emperor chain. But they're there, and there's a bunch of little ones out there. But wow, what's that thing? Well, that's called Shatsky Rise right there. We're going to talk about that. That one's called Hess Rise. There's the Mid-Pacific Mountains. And there's these big complexes, big volcanic mountains out there that are much bigger than anything else. And again, how the heck did they get out there? Well, that's something we would like to know. So just, sorry about the geology primer here, but when I say the biggest single volcano, what do I mean by that? Well, this is typically what we mean by a volcano. It is magma and lava come out of typically a central vent and they come out and they form a conical landform, and we would call that a volcano. If we had a whole bunch of them together, maybe we would call it a volcanic complex. And so what do we mean by magma and lava? Well, you probably are very familiar with lava flows. On the right there's a Hawaiian lava flow from the air. You can see a vent where there's a lava fountaining out because of the gas in the lava, then it's running down like a river over the landscape, and it eventually builds up the volcano, lava flow by lava flow, that cools down. And on the left-hand side, you see an up-close picture of a lava flow, a little lobe of a lava flow that'll go out and solidify, and the next one will come down and bury it, the next one will come down and bury that, slowly building up the volcano by the stacking of these lava flows. So are all volcanoes the same? Well, no, they aren't. On the right-hand side, we see what's called a stratovolcano. They're typically very steep-sided, very pretty volcanoes. Mount Fuji is one of these. They're built up by alternating layers of ash, which is broken up lava, ash and lava. On the right-hand side is, I can't pronounce the name, but it's an Iceland volcano, and notice it has this shape of like an inverted shield, so they're called shield volcanoes. And they're typically made out of basalt, whereas the Arenal volcano, the stratovolcano, is made out of andesite. In the oceans, mostly we have basaltic volcanoes. So here's Mauna Loa in Hawaii from the air, and that is the largest active volcano, and it's also a shield volcano. You can see the shape. Basaltic lava is not very viscous, and so when it degasses, it forms these fire fountains maybe, but it doesn't blow up like the Yellowstone volcano, like the andesite volcanoes. And so typically what happens is you get a vent and lava flows roll out from the vent and they slide down the mountainside and build it up. And if you look over here on Mauna Loa, for example, you can see a lot of the eruptions happen here on the rift zone. You can see a lava flow going down the side of the volcano there, one coming down over there, and that's how you'd expect these volcanoes to build up. So oceanic plateaus are a different thing. There's those big things we're talking about. And the one that I'm going to talk about is Shatsky Rise. I pointed out Hess Rise, the Mid-Pacific Mountains. The largest one in the world is Ontong Java Plateau over here, which is about the size of France. Then there's several others, Manahiki over here, Magellan right in there. But they are big and they look different. Notice lots of these little volcanoes. Little. They might be 20, 30, 40 kilometers across and a few kilometers high. By contrast, these are hundreds of kilometers across. No higher, but still hundreds of kilometers across. So how did those things get out there? They have areas that are in millions of cubic kilometers, or square kilometers. And one question we would have is, do they form like the common seamounts that we see everywhere? Most seamounts form at plate boundaries. So we have a plate, we have plates being formed at the mid-ocean ridges, and so we get volcanoes formed at the mid-ocean ridge. In fact, the mid-ocean ridge itself is in essence a huge linear volcano. We also get volcanoes where plates come together at convergent margins, boundaries, and make volcanic arcs. So that's the two big source of plate tectonic volcanoes. But when we go to the middle of the oceans, there are some that are formed in plate interiors, not at the edges, and Hawaii is a classic example of one of those. And it's thought that Hawaii formed over what we call a hotspot, an area of melting beneath the plate, and as the plate drifted over the top, it forms a chain of volcanoes. And if you look at this diagram in the lower left, you see the ages of the Hawaiian volcanoes, and you see Hawaii is essentially zero age. And the farther you go up the chain, the older the islands get. You go to Oahu, it's 2 to 4 million years. You go to Kauai, it's 5 million years. But Hawaii itself is still active with Kilauea volcano here and Mauna Loa volcano over here. Now here's also another important point. Mauna Loa volcano right here, come on cursor, that is the largest active volcano in the world. And it's sitting in the middle of this island, but there are actually 6 if you count Luigi volcanoes as a part of this complex. There is Mauna Loa, well, maybe we won't see that. Okay, there's Mauna Loa, there's Mauna Kea, Mahukona, Hualalai, Kilauea over here, and then Loihi is an active submarine volcano just off the flank over there. So even though Hawaii itself is a big volcanic complex, it is not a single volcano. And I say that because we're going to go see a large single volcano. So where does Hawaii come from? So 30 years ago, the idea was introduced that it came from what's called a mantle plume. Deep inside the mantle, hot material would rise buoyantly in a column like you see here, and when it got to the surface, it would cause an eruption. And so this mantle plume idea has stuck around for a long time. There's a lot of debate about it, and in fact, that's one of the primary hypotheses for how we get these volcanoes at the Earth's surface. But it can't form all of them. A lot of the volcanoes just don't fit this hypothesis very well. For forming the oceanic plateaus, one very popular idea is that they form by what's called a plume head. So the plume forms at the core mantle boundary at the bottom there, at the yellow part, and it forms a big buoyant blob, and that blob rises up through the mantle. There it is right there, as a plume head. And when that arrives at the lithosphere, it causes a huge eruption, and what we call a flood basalt up there. Basically a large eruption that covers a large area. And some of these have been actually associated with mass extinctions, like the Deccan Traps formed at the same time the dinosaurs died out. The Siberian Traps in Russia formed at the same time, the greatest mass extinction of all time in the Permian, at the end of the Permian. And then it's thought that after you get the plume head exhausted, that then you have this plume rising up through the mantle, and then you get the plume tail, and you get a series of seamounts coming away from it to form a volcanic chain. Now the only problem with that is that nobody's yet actually documented that. There are big oceanic plateaus and there are seamount chains, but no one has actually been able to connect those. So this is a very popular idea, the plume head hypothesis. It's widely accepted, if for no better reason than it's an easy way to explain that suddenly you have this big eruption. But there are others who disagree. As I say here, the trouble is there is yet no incontrovertible evidence that this is right. And some scientists question the number or even existence of the mantle plumes. Maybe there's only a small number of mantle plumes. And other researchers suggest that it may be more complex. It may not be just thermal plumes, but there may be thermochemical plumes. There may be plumes of different sizes and different types. The biggest thing is we just really don't know what's going on deep within the Earth. So we have to take whatever clues that we can get. So Shatsky Rise is the oceanic plateau that I've been studying. And the question we went out to try to address is, was it formed by a plume head or some other mechanism? Now Shatsky Rise has some of the characteristics that you would expect for the plume head model. So on the right-hand side is a plume head model. You see the blob, and then you see it coming up to the lithosphere, and it uplifts the lithosphere, and it causes a big eruption. And then on the lower right over here, you see that idea that it forms a flood basalt. So that would be the biggest eruption at first, and then it would trail away with time with smaller eruptions. And we see that at Shatsky Rise. The oldest volcano appears to be big, and then it gets smaller as it moves along. So we thought also that it might show uplift because it must have stuck up out of the ocean. We were going to try to test that. It looked like you had this transition from the plume head to smaller volcanoes, the plume tail. It obviously had to have a large source volume, so all that seemed to fit. But there are some other things that didn't fit. One idea is that if you have this magma that comes up from deep within the Earth, well then you ought to see a signature that looks like it came from the deep mantle. So geochemists, and I'm not a geochemist, geochemists still argue about what that might be. And so that's a problem, but everything that all the rocks we have from this place look like, well, they look like the mid-ocean ridges, shallow, not volcanism, not deep volcanism. Also, this thing formed right around the time of the Jurassic Cretaceous boundary, and even though there is a boundary there, there's no obvious mass extinction or that you might expect from such a large eruption. So that part of the puzzle doesn't seem to fit very well. So there are some pieces there and some pieces that aren't there. So here's a bathymetric map of Shatsky Rise, and you see the different names. So Tamu Massif is the large one on the bottom, Ori Massif, and then Shearshock Massif. And then you see a ridge tailing going off to the northeast. Down over here on the very lower left is a typical large seamount. And so you can see how much smaller it is than Tamu Massif, for example. So this whole thing has an area about the size of California. Tamu Massif itself has an area about the size of New Mexico. So it's a big thing. So we see these blobs. And so a long time ago I thought, gee, that looks to me like one volcano, doesn't it? It's one mound, so it must be one volcano. But what would happen is when I would tell that to other scientists, they would go, no, you can't say that. It could be, these things must erupt on fissures. They must be multiple eruption centers. So it'd be more like Hawaii. Lots of volcanoes that are all strung together. So I couldn't prove that for many years. But we'll talk about that a little bit later. A little bit more about the size here. So there's Tamu Massif, the kind of big green blob on the lower left. And next to it is Olympus Mons on Mars, the largest volcano in the solar system at the same scale. And so you see they're not that different. Olympus Mons is still the largest, but Tamu Massif isn't far from it. Now, to be fair, Olympus Mons is 24 kilometers high, but Tamu Massif is only 3 to 4 kilometers high, except that Olympus Mons sits on very thick, rigid lithosphere, so it's mostly above the surface, and Tamu Massif is like an iceberg. It's 30 kilometers thick, so most of Tamu Massif is down in the mantle. So it looks like one big volcano, but until recently we didn't know what the interior structure looked like. So here's Tamu Massif versus Mauna Loa on a Mercator map, just so you can see the two. You can see how much bigger Tamu is than Mauna Loa. So as I said, we weren't really looking for the biggest volcano. Our project was to understand the origin of Shatsky Rise. And so what do we know about Shatsky Rise formation? Let me give you a little bit of a history of how we think, the clues that we have about Shatsky Rise and its formation. So I understand Dave Rich is in the audience. Dave, I'd be happy to meet you after all these years. Dave, there you are, okay. So when I was a young professor at Texas A&M 30 years ago, one of the first theses I read was one that Dave did. He was a student at Texas A&M and worked for the guy who had the office next to me. And he studied the magnetic anomalies in this area. So Dave, here's the magnetic anomalies 30 years later. What you see is two sets of, you see this is the bathymetry of Shatsky Rise up the middle, and these red lines are the magnetic anomalies from the M sequence. These were formed at the Pacific Farallon Ridge. These over here were formed at the Pacific Izanagi Ridge. So there were two ridges that came together because one went in that direction, the other one went in this direction, and you see they come together right where Shatsky Rise is. And so that's a very interesting observation. It says that Shatsky Rise had to form along the trace of where these ridges met. Where you have two ridges, you actually have to have a third. It's called a triple junction. And so there it is. This is the triple junction before, in this set of plots, the dark shows what's existing at the time. This is M22 time, about 150 million years ago. And so there was a triple junction of three ridges that came together, and it was happily going in the direction of the arrow to the northwest. Let me jump back. I missed something on that slide when I accidentally hit the button. Currently, we only have one radiometric age for Shatsky Rise, and it's where that orange circle is, Site 1213. It was drilled in 2001, and it's dated at 144.6 million years, which is essentially the age of the magnetic anomalies under it. And so what that means is that this volcano had to form right at the same time as those magnetic anomalies. So it had to form right at the ridge. So here's the triple junction at 122 million years ago. It's going to the northwest. And then Shatsky Rise began to form shortly thereafter. A few million years later, at 144 million years, at M17 time. Now you see the triple junctions at the center of Shatsky Rise. It followed the blue arrow. It jumped actually 800 kilometers to the east and then began following Shatsky Rise. More likely what was happening is there was some volcanic process that took the triple junction and stopped it going from the direction that it should go and made it follow the volcanism. And then we go a little bit later, 139 million years and 131 million years, you see that the triple junction follows Shatsky Rise right on up as it forms. And so these large volcanoes were formed in the plateau along the wake of this triple junction. So Shatsky Rise, in some ways, fits the Plume head model. It begins with a massive eruption that is, we estimate, at 2.4 million cubic kilometers. The initial eruption was followed by a transition to a smaller eruptive volume. You saw it go from the bigger one to the smaller ones to the little ridge that goes off to the northeast. So, and also the triple junction seemed to be captured by volcanism. So it seems like there must be some heat there that keeps the triple junction wanting to go. Now remember, what is a triple junction of ridges? It's just where you take three plates and you split them apart, so it's a crack. So basically it's going to follow the line of weakness. Also, we had dredged shallow water fossils back in 1994 from the summit of Tamu Massif, and so we knew that it had been in shallow water. So that suggested, well, it must have been high enough at least to get up to be, maybe it was an island, although we'll get back to that, and I'll disagree with myself here in a little bit. But there were some observations that didn't fit, and one of them is, I promised to only show you this one geochemistry slide. Our geochemists, what they like to do is they like to find isotopes that have different behaviors. So these are neodymium isotopes versus lead isotopes versus strontium and then lead. Anyway, you plot these things and you hope that your samples fall into groups. So one of the groups you see here is the East Pacific Rise. East Pacific Rise is there, it's there, it's there, and it's there. So East Pacific Rise is what you get from shallow volcanism at the mid-ocean ridge. And you'll see that these are the symbols are from Shatsky Rise back in 2005 from that one hole we had. And you see that they plot the same place. So by this geochemistry, it looks very ridge-like. It doesn't look like a plume. So that doesn't fit very well. Then there's just a logical argument. If you have a plume and it comes up from the core mantle boundary, and it doesn't care what's going on the surface, and it just rises up, and there's a triple junction up here, what's the odds that it's going to come up and hit right near that triple junction? Well, the odds that of a plume head, a random plume hitting within 800 kilometers of a random triple junction is about 0.4%. Not very good percentage, okay? So coincidences happen, but as a scientist, we don't like coincidences. Or maybe the plume does know and care. Maybe the plume is following. And one idea is that at a triple junction you have upwelling beneath the ridges, and the plume might come up and follow that in. Here's another interesting observation. So Shatsky Rise is just one of many plateaus, and it looks like many of them fall along a triple junction. So this one triple junction that I mentioned earlier went up this way, got the Shatsky Rise, went over here, eventually went up this way, and we think the lights went out during the Cretaceous quiet period. Come back there. But there was another plateau over here near where it eventually came out. Another triple junction went this way near the Mid-Pacific Mountains, near the Magellan Rise, and near Manahiki Plateau. So goodness gracious, if there's only one, less than 1% chance that a random plume will find a random triple junction, that's an awful lot of coincidences. And it makes me think that there must be some kind of ridge control that makes these things happen. So why study Shatsky Rise? I mean, it's just one of many out there. We went there because it had a couple of characteristics. One is it has those magnetic anomalies that I mentioned. That's rare. It turns out that many of these were formed during the Cretaceous during a period of time when there were no magnetic reversals. So this is the only large plateau that's formed at the time of magnetic reversals. It also has this sort of tantalizing combination of things that fit both of those sort of end-member hypotheses. And so maybe it's a special class of, sorry I didn't explain large igneous province, that's the LIP acronym, formed at reorganizing ridges, or maybe it's characteristic of all. We didn't really know that without going out there. So I was able, after many years, to convince some people to put some money into it. And so in 2009, I was a co-chief scientist for an expedition on the Integrated Ocean Drilling Program. It's still called IODP, but the name has changed to the International Ocean Discovery Program. Okay, got to have a new acronym, even if it's the same thing. And we went out there because we specifically wanted to try to get basalt. There'd only been one set of cores cored from the basalts of Shatsky rise. We wanted to test the age. We wanted to test the age progressions. We also wanted to look at the geochemistry. We wanted to look at evidence for paleo water depth. So this was 15 years in the making. I first submitted this proposal in 1995, shortly after my first cruise, and it was finally granted in 2008. So it was a long time coming. So there's a photo to prove that I was there at the drill ship. And so we went out and we drilled, where you see the red dots are where we drilled. So we drilled one up on Shearshoff, two on Ori, two on Tamu, and then we already had the one called Site 1213 that was drilled in another expedition before that. There are a bunch of other little holes that have been drilled, but none of them had gone into the igneous part of the volcanic complex. So we wanted to, and that was particularly what we wanted to look at. So once again, this is the bathymetry map, and it shows the magnetic lineations around it. And one interesting thing is that notice how the magnetic lineations go through parts of Shatsky rise, which is really interesting. It doesn't go through some parts like the middle of Tamu, but it goes through the flank of Tamu. So that suggests, again, a link with the ridge formation. So when we drilled at Shatsky rise, we found massive flows. So these are the different sites that we drilled. And I know you can't see it all at one sitting here in the short time I'm going to show it to you, but these are the different sites. These are Tamu Massif right here. This is another plateau called Ongtong Java Plateau. This dark green here represents massive flows. These are flows that are tens of meters thick. This lighter green, here, come back arrow, that lighter green represents pillow lavas. They are the sort of normal low effusion lavas that form undersea. It's sort of like squeezing toothpaste out of a tube. They come out like that, and they form little things that look like pillows when you cut them open. And so what we found was that at Tamu Massif, right over here, this one we just got explosive volcanism. But here we found alternating massive flows. Here we found massive flows, and very similar lithology on Ongtong Java Plateau, which is the world's largest plateau. And the thickest flow that we found here in this short section of about 150 meters that we were able to drill into the igneous part, 23 meters thick, that's 75 feet. So think of a lava flow 75 feet thick on the flank of a volcano. Suggests that you have to have a massive amount of magma pouring out, lava pouring out in order to do that. There's no reason to think that there was a pond of lava. We think that there are lava flows because as we drilled this on the flank. This is what one of those massive lava flows look like in core. So that's a core. It was a 9.5 meter core. You're seeing half of it's been split. So it was cylindrical, it's been split, and you're seeing it, sections of it laid out. And mainly what you see is it all looks the same. That's because it's very homogeneous inside this massive flow. So important points from drilling that we learned is that Tamu Massif looks like a typical flood basalt. I forgot to mention those massive flows are seen on land. They're seen on lands in places like Deccan Traps, the Siberian Traps, and other places where flood basalts have happened. So we see the typical lava flows from flood basalts, and we also make the connection with Ongtong Java Plateau. So it looks like their formation mechanisms are similar. The one thing I forgot to mention on that is that you didn't see those massive flows when you go farther up Shatsky rise. So there does seem to be a transition from massive flows on Tamu to smaller flows as you go up to the smaller edifices. So there's, there does appear to be a waning of volcanism, or at least a diminution of the effusion of magma coming out. Also, wherever we drilled, we found evidence that wherever we drilled near the summit, we found that we were getting shallow water sediments. We didn't find any strong evidence of actually being subaerially exposed, but we found lots of evidence for shallow water. And then again, from the geochemistry, nothing really looks that much different from Ontong Java or mid-ocean ridge basalt. Sorry about the acronyms. MORB is mid-ocean ridge basalt. Okay, so I mentioned seismic in the title. Yes, there's seismic data. So actually, after the drilling crews, and this could only happen with the government, right? Because I'd been trying for about 5 or 6 years to get the U.S. academic seismic ship out to Shatsky Rise to get new data to see inside the thing. But we got the drilling proposal funded with only a year's lead time, and we couldn't get out there. So then the next proposal I said, well, we got the drilling, we really need to get the seismic data. So then I got it, and so I was able to go out and collect the seismic data the year after. Anyway, and it was on a ship called the Marcus Langseth, which you'll see here in a moment. Yeah, there's the Marcus Langseth. If it looks vaguely familiar, it ought to. It's actually an old Western GECO ship. And it had been sitting around for a while, I think, because it's just covered with rust. This was the first cruise out of dry dock when they were fitting it up. It looks pretty from this angle, and there's a rainbow there. It's in Honolulu. The guys I felt sorriest for were the poor seamen that had to paint, because every day I would go out there and they'd be on there, they'd be painting, and they're trying to paint over all that rust. And if you ever seen a seismic ship, it's got a million interstices and cracks and in places where rust can hide. I really felt sorry for those guys. But anyway, so we got to go out on this ship. But there were some wrinkles with this cruise because, like I said, it was the first cruise coming out of dry dock. So I'm going to tell you about some issues that came up. All the cruises but mine got canceled. Why did mine go forward? Because it was funded with ARRA, the Obama's recovery money. So NSF got a little bit of money. They put it into this cruise, and they couldn't cancel it because they had to spend it. Anyway, so we had to go from Honolulu, which Honolulu is a great place to go. I highly recommend it, but it's 10 days away from Shatsky Rise. So we had to sail 10 days out to get there. We had to sail 10 days back to get there. So there's 20 days to start with. And then this cruise was the unluckiest cruise I've ever been on. And I've spent probably about 4 years of my life at sea on various cruises, 41 cruises. Cruise was delayed 6 weeks in the shipyard. Delayed another 2 weeks because of engine control problems. Seismic ships, they have to have precise engine control. The cruise was assigned 20 days of transit because other cruises were postponed. So the cruise, not only did it shift by about 2 months, it also grew by 20 days. One of my colleagues, who was a seismologist at Lamont Doherty, passed away from a heart ailment in the middle of the summer. I suppose the lucky thing is that he would have been on the ship, but I guess it wasn't really that lucky. But anyway, the cruise was delayed 2 days waiting for incidental hazard assessment. And those of you in industry might recognize that's your permission to go out and annoy the whales. The cruise was delayed another 10 hours because of a technician's plane being late. And then we got out and started doing our work, and then we had another death. We had a senior marine mammal observer passed away from a heart attack. And so we had to take his body to Japan. So Japan is 4 days away. So we went to Japan, we dropped him off, we came back, and we started working. Then we had a second medical evacuation. It was the captain's first time being captain. I think he was so traumatized that the cook had a problem with his leg, and he was afraid that the cook might have phlebitis, I think, and so we took off again and back to Japan. But we didn't actually go into the harbor this time, so it was only 7.5 days. So At the end of the cruise in September, they got a Hawaiian kahuna, which is a religious shaman, to come and bless the ship and chase away the evil spirits. And the project was finished actually 2 years later, after the grant money had already run out. 2 years later, they gave us another short cruise to go back and finish it. Like I say, this can only happen with the government. So our survey plan looked like this. The blue line was a seismic refraction line that we shot across the center of Tamu. The red lines were all multi-channel lines. Basically, the ones on Tamu we did in the first cruise, and then we went back and to finish up the northern part of Tamu and to go across Ori on the second cruise. The MGL 1004 is the 2010 cruise, MGL 1206 is the 2012 cruise. And I'm glad that NSF stuck with us and gave us another cruise, which was very expensive, because I don't think had we not had the data from the northern part of Tamu that I would have been able to get this paper published in the prestigious journal that I did. So here's a quick snapshot of the OBS data published by a colleague of mine, and what you see at the top is a cross-section of Tamu Massif, and that's a velocity profile on the upper left that says C there. And so basically what you see is Tamu Massif is this low rise with like an iceberg keel at the base. So it shows that Tamu Massif is huge. It's very thick, but it's just most of that is hidden beneath the crust. Now I'm going to start showing you some seismic profiles. The bright red line shows you where this one's going to come from. I'll show you a close-up of one line to show you what we're interpreting. So on the left-hand side is raw data, and on the right-hand side is interpretation. And what you see is, if you look at the top part, you see nicely layered sediments. That's what you'd see if you were looking for oil. Of course, there's no source rock around here, so that's not a worry in this neighborhood. And then you see these sort of lower frequency, but clearly layered sequences much deeper in the section. And those we interpret as being the tops of lava flow packages. Now, one thing I have to mention about this is that by the time the seismic wave gets into the igneous crust, we're looking at wavelengths that are probably on the order of 100, 150 meters, something like that. So we're not going to detect an individual lava flow. We're going to detect changes in lithology related to lava flows, and I'll show you that in a minute. But the exciting thing here is that you're seeing reflections from things that we can interpret as lava flows that are more than a second deep in this one right here. We've seen them as deep as about 2.5 seconds, which is 4 to 5 kilometers deep inside the volcano, which is really outstanding. So this is, we did get some logging data when we went drilling. So on the left-hand side is a lithology for one of the sites. We went across the sites with our seismic, and then you see a velocity and a density log, and then you see a synthetic record, and then you see on the right-hand side the actual multi-channel traces. In essence, what you're seeing is we have the top of the igneous basement is right there. It gives us a big reflection because there's a big rise in both density and velocity. And then you get to a section of pillow lavas where you have lower density material. There's also a few sections where we have the red arrows, or where we have sediment layers that are intercalated that are approximately 5 meters. And so you see a low velocity zone in here, another low velocity zone in here. That basically gives rise to your reflections, those gradients in there. And we get a pretty good, our synthetic matches the actual traces pretty well, except for this one spike right here that gives us a reflection on the synthetic but doesn't appear in the actual multi-channel traces. And who knows, that could be some bad data points in the log, or it could be that very thin layer that shows up in the logs that doesn't show up in the seismics. Really can't tell. Now let me show you a line that goes all the way across Tamu Massif. This is our most complete line. And so this is Tamu Massif in profile. And so what you see is a large rounded mound. And I should tell you that the vertical exaggeration here is about 30 to 1. So it looks steep, but it's not at all steep. Up there you see the seafloor slope, and most of the slopes are a degree or half a degree or less as you get down on the lower flanks. It is the slopes are so shallow that if you were blindfolded and walking across it, you'd have trouble telling which way is down. Shoot, without the blindfold, you might have trouble telling which way is down. One very interesting thing here, so this is the interpretation down here. These are the lava flows that you see here and here, and this is a late stage volcanic peak that sticks up. You'll see it in some subsequent figures. That's sediments on the top, but you see, what you see is this broad dome, and we see the lava flows come out and go that way, and they come out and they go that way. There's no obvious secondary source of volcanism except this very late stage thing here. And we won't see that on other profiles. And if we look at the pattern of lava flows, they go kind of pretty much right on through it. So that is the evidence for which we say that it looks like this Tamu Massif is a central volcano where the lavas come out from the center. We'll see other profiles. And basically, the main point is going to be that no matter how we cut this thing in half, we're always going to see the same picture. Okay, so this next profile goes up the length of Tamu Massif, kind of a convoluted profile, but we were trying to follow the axis. And so you see a similar sort of pattern. You see a broad dome, and you see lava flows that go in places very deep. Now there are some places like these arrows down here, there are local highs that maybe they were a center at one time, but most everything comes from the top of the volcano. So that last profile cut across right about there. And so you saw that same pattern in two different directions now. And you can see there are things, here's some buried cones right there. We found lots of cones. There is another cone that's buried over there. There's another one on the flank over there. This next profile is going to be down on this side, on the west side. And again, you see a very similar pattern. You see some interesting faults in here. We still don't understand these faults. But they appear to have happened later. But basically you see a big mound with lava flows going away to the sides. And then this one goes across the north side. And once again you see the same sort of picture. There is the sediment cap right there. Now I forgot to point this out on another one, but there is a caldera right there. So that in many volcanoes we see a caldera at the summit. If you go to Kilauea or Mauna Loa, you'll see a caldera at the summit. So we found a buried caldera in there. And we do see one of the interesting things, because this thing is so low and so broad, these secondary cones look like major mountains, but they're not. They're a few tens of kilometers across, maybe a kilometer high, sitting on the flanks, and they look like these daggers sticking out, but it's just because the vertical exaggeration is so high. But once again, lava flows go that way, lava flows go that way. This one goes across Ori Massif, which is the other one, the next biggest one, and it's basically a similar pattern. We see it looks like it's symmetric around the middle. And so no matter where we go, we see that same picture. So that's the origin of the idea that we're looking at one massive volcano, and probably Ori is one massive volcano. So this thing, whatever mechanism made it happen, it can generate huge volcanoes in one place. This slide talks about about how shallow was Shatsky Rise. How shallow was the top of Tamu Massif? One idea is that, remember, if you had this big blob coming up from the Earth's, buoyant blob coming up in the Earth's mantle, it ought to push things up high. Iceland today is thought to be at the top of Mantle Plume, and it sticks up, it's a high island, it sticks up by a kilometer or two. So did Shatsky Rise do that? The answer is not really. So in these diagrams, what we plotted is, this is the depth where we drilled the volcanics in each diagram. These are different holes, one for each hole. This is backtracking as lithosphere ages, it subsides. And so these are the subsidence models, curves for that. And you see they all backtrack up so that they're in pretty shallow water. Remember, when we drilled, we found shallow water sediments, but no evidence of emergence. And so, indeed, that's what that fits the analysis of the sedimentary data. And also, look at this profile. This is that same profile again. If you look at the Hawaiian volcanoes, they come out of the water, and within a few million years, the waves plane them right off, and they're gone. We don't see any of that. There's no evidence for subaerial for wave erosion at the top of Tamu Massif. And what's more, this thing actually sticks up. So we think that this thing formed first, the main peak. This one must have formed later after it has subsided, but neither of them show any evidence of wave erosion. So we think that it was never highly emergent. So that doesn't really fit the plume model very well, or at least not the classic plume model as being a thermal plume. Okay, so let me summarize a little bit. So why is the world's biggest volcano important? I got that question a lot. It was important because it got the paper published, okay? So that was the immediate thing. And then I had to think about, all right, so why is it really important? Okay. Tamu Massif is vastly larger than the common seamount. So it's a different class of volcano. You saw all those little seamounts, little pimples all over the place. This is a much different thing. It has a different morphology. Instead of peaked, it has a very broad shape to it. It indicates lava flows. We think that indicates lava flows that travel long distances, very fluid, very massive lava flows that basically go long hundreds of kilometers. And so we have high fusion rate, low viscosity flows. So why is Tamu Massif a single volcano? As I said, it has a large emplacement at the single near the center. And why do we see that? Well, we think that what happened was the plate was drifting over this source, and it formed Tamu, and then the plate that drifted away, and then it formed Ori, and then it formed Shearsoft. So there was a gap, and the plate moved in between, just like there is in Hawaii, except on a bigger scale. So what does Tamu really mean besides the acronym? Plateau formation relies on a large extraction of magma from the mantle. Typically, we think at the base of the mantle that there might be partial melt of a couple of percent, 2-3%. You have to, even at 10-20%, you have to evacuate a tremendous amount of mantle to pull that amount of magma out of the mantle. They are similar flows to continental flood basalts, that's the CFB, and Ongtong Java Plateau, and that suggests a common link that's been suggested for these. And so oceanic plateaus can have these single sources, and the single edifice can be much larger than previously thought. As I said, until this time, we really didn't know of volcanoes of this size on Earth, so that's one of the reasons why it was important to recognize this. Kind of like we're going to have a dinosaur lecture. It's kind of like we found a T-Rex that's 10 times bigger, actually 50 times bigger than the other biggest T-Rex that we knew about. So what about this argument of is it a plume or is it a plate? Well, the jury's still out. There is no one observation that clinches the argument. But this is the way science works. We're going to chew on these data for a long time. I'm a geophysicist and I can see what's at the surface, and all I can tell you is what the volcano looks like at the top, not where it came from down below. So maybe the massive size, that suggests to a lot of people that it must have been a plume. You got to bring up some heat or something to make it happen. And it fits the plume head to plume tail model. That's still there. There's a strong link to spreading ridges in a triple junction, and so there's a link to plate boundaries. And so the idea that these things are disconnected, maybe that's just wrong. Maybe there is a connection. Maybe we just don't understand that connection yet. Geochemistry so far is still similar to Ongtong Chava and Mid-Ocean Ridge basalts, but my geochemistry colleagues are arguing about what that means. Some say, well, you can see the same variability, you see the same things on the Mid-Ocean Ridges. Some say, no, it's only, anyway, it's over my head, and I'm waiting for them to come to decision. And like I say, perhaps we just don't understand the problem. We have a tendency to go out and say, well, it could be this, or it could be that. And reality is it could be something else that's maybe related to both of those things. So the story was, of course, one of the big things about this. It was a great opportunity for outreach. I've done many things over 30 years of my career, and actually until this time, the funny story is, my biggest claim to fame was seeing a squid. So back in 2000, I went down, I was studying oil seeps in the Gulf of Mexico. I went on a dive on the Alvin, and we got down to the bottom, and if you've ever been in Alvin, it's this little 6-foot titanium sphere, and the only person who can really see is the sub-pilot. So we get to the bottom, we flip on the lights, cruise around a little bit, and the subpilot says, "What the heck is that?" And that's not what you want to hear about the ocean. So he got the video camera on it, and I'm looking over his shoulder, and there's this weird squid there. And unlike most squids that take off, it just kind of slowly flapped like, hey, submersibles happen all the time. It had these spaghetti-like arms. I took videos of it, then we went on and did our business. Later on, I gave the videos to a guy at the Smithsonian. I ended up being 7th author on a science article. And I don't know why, people called me. And I was on TV, on CBS, on NBC. I was in the newspaper. Even local news and College Station thought they better interview me. They don't like to really bother people with science. And so that was great. It was great, except I kept saying, I'm not a cephalopod biologist. And no, tell us about the giant squid. No. This is something I actually did, so I'm proud of that. It was a great opportunity because it had that little hook, biggest volcano in the world, that made people go, oh, and they would look up from their smartphones for a few seconds. And it also showed a huge difference in the way that news had changed in the intervening 12 years, 13 years. Back in the old days, it was newspapers and TV. Now it's all the web. We put out a few press releases. IODP did one, UH did one, Texas A&M did one, and those things got copied. Eric Berger in the Chronicle did an article. There's a few newspapers did interviews and did articles, and then those things got cloned all over the webs. And we kind of lost count at about 400 web articles, something like that. So it was great. UH was just loving it. Tamu was just loving it. Story appeared on like 400 websites but maybe there were only about 15 different interviews. It's always interesting. On both of these things, I get interviews by talk radio. I guess talk radio has airspace to fill, and so they call people like me in the middle of the night and I don't know, keeping people awake or something. The story appeared on TV mostly as a short headline, often attributed to scientists without mention of the affiliation. And one of the things that I did in all this was try to spotlight the IODP and also the National Science Foundation, because both of these things, the ocean drilling program and this seismic ship, are under intense budgetary pressure, and they're not a given that they're going to stick around. And very nicely, it was also ranked by Discover Magazine as the number 11 in their top 100 science stories and the highest ranked geoscience story for the year. So that's neat. It's on the wall of my office now. There's also just weird stuff. Somebody wrote a song on YouTube. I guess that just proves that some people have more time on their hands than they really need. There was a story in The Onion. So The Onion went out, and I don't know whether it's real or not, but they had interviews of 3 people on the street, basically proving that they knew absolutely nothing about this. Yeah. I got hate mail. Somebody objected really strenuously to the fact that I named it Tamu Massif after the Aggies. And it wasn't even a Longhorn. It was from somewhere in Washington State. And it's just that, I guess I should feel lucky that it was only one bit of hate mail, because, anytime you look at any story posted on the web, the people who are off their medications come out and they make all these rude and inappropriate comments. Anyway, and my sister tells me that she was watching a program that I've never seen called Million Second Quiz, which I have no idea what that is, but it must be a quiz of some site. What did scientists recently discover the largest of? So it even made it onto a quiz show. So anyway, I think that's it. So I'd be happy to answer questions. Thank you. Yeah.
I noticed on many of your seismic profiles, not all of them, but the majority of the seismic profiles you showed had the thickest sedimentary overlay at the crest of the structure, suggesting that the initial growth started from a basin.
You mean initial growth of?
The massif itself.
Well, the sediments accumulate unevenly for 2 reasons. One is that currents swirl around the summit, they tend to clear it off, but also it's above the calcite compensation depth. Once you get down to 4,500 meters in the Pacific, all that carbonate is going to go away. And those are largely carbonate sediments, pelagic sediments on the top.
You said 2,500 meters?
What's that?
2,500 meters?
40.
I think 4,500 is, I don't know exactly because I'm not a chemical oceanographer, but I think it's 4,000, 4,500 meters is CCD in the Pacific. Yeah, I'm sorry, somebody back there. Yes?
Interesting talk.
Thank you.
Not all mid-ocean rich basalts are similar. Have you done detailed geochemistry or ratioing, and have you looked for refractory trace minerals in the basalts?
I remember, I'm not a geochemist, and my colleagues are doing that. If you're interested, give me a card and I can get you the papers. And yes, they're looking for not only at the major elements, but also at trace elements, but also at the different flavors of isotopes and their ratios. Yeah.
Is there any way to tie energy and minerals to your research, like finding rare earth minerals or gold?
Well, in the Gulf of Mexico, most certainly. So one of the things I study is the Gulf of Mexico, and so I have trouble holding on to my students for very long because they're all off working for oil companies. In this area, there's really not there's no hydrocarbons because there are some. The sediment cap does have some black shales, but that's about as close as it'd never be economic to go after them. And manganese nodules it's covered with manganese nodules, but so far it hasn't proven economically feasible to dredge up manganese nodules. Not to mention the environmental disaster that it would be to like scrape them all up off the seafloor. But that people have been researching that for a couple decades, but nobody's actually done it yet. Yes, good.
Have you done any heat flow studies using satellite data to see if there's any remnant hydrothermal activity in the area?
Thank you for asking that because you reminded me that I forgot a very key thing. Remember, this thing happened 145 million years ago. It is as dead and stone cold dead as any volcano can be. But no, nobody's done any heat flow on it that I know of. But there's also no reason, they would never get the funding to go out and do it because, oh wait, actually I'm wrong about that. On one of the holes drilled, I think we took some temperature readings, and it's just it's an old ocean heat flow. No real heat source there. We did find a lot of evidence of hydrothermal circulation in the basement rocks, suggesting that when it formed, there was lots of heat and lots of circulation of seawater, probably through cracks that deposited and leached out a lot of minerals. So you could see a lot of these. And of course, our geochemists hated that because it just wreaked havoc with the chemistry of the rocks. But no, nobody's looked at it for any recent heat flow. Yeah, Dave.
I'm glad to see that research is continuing in this area years after I looked at it. And I'm glad it's getting a lot of recent publicity. Thank you for that. One of the things that we looked at when I was working the problem was the two plates, the Carolina and the Kula, were moving at about the same rate along a fracture zone there that eventually the plateau developed on top of.
Right.
And the idea was that because it's moving at the same rate, that it's a stable configuration, and that would have given, if it was a leaky transform, that would have given an opportunity to create huge amounts of outflow. Is that still something that people are thinking?
It's still basically correct, and I only gave part of the story because it was the simplest part. When I said the triple junction should have gone to the northwest, that was the direction it was going because you can see that with the magnetic bites, but that's also the stable direction if it's a ridge, ridge, ridge. If it's a ridge, ridge fault, which is a possibility, then it could have been going in, I think it would have been going, I don't remember, it's been years since I looked at it, but I think you're right about that. And I ignored that part. Part of the problem is that all we have left is a record on the Pacific plate, as you know, and so we don't actually know what was on that other boundary. We can only speculate. It's all been subducted beneath Asia. Yeah.
Are you going back to the same area, or what's
Well,
next?
actually I am, and it's another weird twist of this tale. So I figured there's no way I'm going to get NSF to give me any more money to go out there. They've given me millions of dollars to go out with these two cruises. Somebody else's turn. And also, to get NSF funding, you have to prove that something is transformational and not just the next step. But there are Google billionaires that have made an oceanographic institution in California called the Schmidt Ocean Institute, and they have their own ship. And so last year, I saw a call, they said, send us your proposals. So I sent a proposal to go out, and the thing that, Dave, I want to do is, magnetics have been ignored through all of this. The problem is that most of the data that were collected that have magnetic data out in that area were collected in the 60s and 70s. There's really not much new data. So I said, we really need to go out and look at those magnetic lineations and how they come together. And lo and behold, they say they're giving me a cruise. But here's the interesting part. I don't have any money to get there. I don't know I'm going to get there or bring my magnetometer along. But that's details to be worked out later on. So next year, next summer maybe, I'll be going back out again. And I did get an outreach coordinator we're going to try to get hooked up, so this time beforehand, maybe you can come along and watch us on the web. It's Google, remember, so they got a good web connection. Yeah, amazing.
Yeah, that was something I mentioned at dinner is, you know, when you go to Google Earth and you open up the bathymetric picture of the Earth,
right.
It just seems like we know everything. You know, everything looks mapped and it looks clear, but in fact, probably the data for each of these areas varies, you know, tremendously between, you know, how much control we really have and what we really do know. And so
right.
how do you, I guess, how do you recognize that or reconcile that when you're going in and exploring inside Google bathymetry? You know, how well do we really know areas like that?
Most of the Google bathymetry comes from a satellite measurement. And I know I told you earlier that you can't do it with a satellite, but you can fake it. And so what they do is a satellite flies over the ocean and it uses a radar beam, a microwave beam, to sense where the sea level is. And so it's a big spot, so it's not, the waves are averaged out. And that's an equipotential surface. Basically, it's gravity. And so they can derive the gravity in the oceans, and from that, making some assumptions, they can derive the bathymetry. And so what they've done is they've gone through, used actual bathymetry soundings plus this gravity, and done basically a transformation function to convert gravity to bathymetry. And so that's mostly what you're seeing. The great thing about that is it fills in all these gaps. And it's pretty good. It's really been shown to be pretty good, but it doesn't have much detail. Actual modern bathymetry soundings that we have, in the old days a ship would go over and just take a sounding. Nowadays a multi-beam ship goes over and does a swath of soundings. And we have maybe 20% of Shatsky ride covered with actual real data. The rest is filled in with the satellite. And so there's still a tremendous amount to be learned. In fact, we'll collect more bathymetry data on this next cruise. It is one of the frustrating things about being a deep ocean marine geophysicist, because in areas like this is actually well surveyed. Go to the Southern Ocean, there are whole states, there are gaps that are big enough to throw, well, maybe not Texas, but there are gaps big enough to throw a large state in and not hit anything. And it's just because they're a long way from anything, and most of the exploration done in the oceans was done in the 60s, 70s, and early 80s. Since then, it's all been very targeted. And so not only is it not much data, but most of that data is old data that's very badly navigated, long before GPS. So half the time we don't know really where we are. Oh, yeah?
So in one of the typical maps that you showed earlier on, it looked like several of the oceanic plateaus were several times larger than the Tamu Massif.
Right.
So shouldn't we view the oceanic plateaus to be the really anomalous things? Because these are massive areas that are up.
Sure.
with processes.
I guess I would say it depends on how you define anomalous, but I would say yes, probably so. They don't fit within our classic plate tectonic. So if we use that as our baseline, yes, they clearly are outside that, and that's in fact why I get to study them, because they are anomalous. And so you're right. And another point a good point to make is Tamu Massif is just one part of Shatsky Rise, and it's the biggest volcano that I know of. There are bigger plateaus out there. I'm very curious about Ongtong Java. Like I say, it's this big roundish thing the size of France, but nobody has got enough survey data over it yet to say with any certainty is it one or many volcanoes. That's our classic problem with studying the oceans. Going back to Denise's question, I get this all the time from reviewers of articles. I spend 2 months at sea and I have a few postage stamps. Then they say, well, you only have these small areas. How can you make well, my job is to do that from the small postage stamps. That's right. That's geology, isn't it? And marine geology is especially bad because we never have enough data. But that doesn't stop us. Yeah.
One more question.
Yeah.
Has there been any hypothesis put out that these plateaus might have originally been the cores of cratons in the early primordial Earth?
That is certainly one idea. And it's obviously hard to prove because if it's a craton now, it's been so massively metamorphosed and mushed around that it's hard to say. We think that these plateaus, they are too buoyant to subduct. So when they hit the edge of a continent, they'll just get scraped off into the continent. And so that may well be exactly, that's one idea of how you get your old cratons initially. Yes, one more question.
Is the magnetic and gravity data a match for what you're expecting from the seismic compositionally?
Okay, I'm sorry, I didn't quite catch that. Could you repeat it again? I sort of missed it.
Is the gravity and magnetic data a match for what you're seeing from the seismic? That's
actually a really good point. Maybe not. The gravity doesn't show. Well, one very interesting thing about the gravity is that this thing is so isostatically compensated that there's practically no gravity anomaly. And I had 2 master's students work on a gravity model, and they both came up with kind of different conclusions. So okay, I'll have a third do it, then I'll take the average, I think. But one of the things about the magnetics is, remember I showed you that there are places where the magnetic lineations go through. We wouldn't expect that if we have a volcano that spews lava over large distances, because Iceland forms at the mid-ocean ridge, and we do see the magnetic stripes come up and they get wiggly, but they go through. And what's happening there is the lava is coming up in volcanoes right along the rift, and then they split and they go their different ways, but it's not like this. And in fact, that's the basis of my latest proposal, is we need to find out why. We need to look at that transition between where we think we have the magnetic stripes and where we don't, and see if we can figure out a good reason for that, because it suggests that this thing is maybe half and half or something like that. So that's a very good point, but no, it's not all tidy yet.
Very good. I think
Well,
we had
thank you,
some good
everybody.
discussion. If you have more questions, stick around after. I think we'll be
I'm happy
willing
to answer
to
questions. Sure.
answer some more questions. We'd like to thank you for coming out this
Oh,
evening.
thank you very much.
We have a little gift for you. It's a
thank you.
paperweight, so you'll remember us and maybe
Oh,
come
how could I
back.
forget?
Come back and give us another chapter.
Okay,
Yeah.
certainly.
Thanks very much.
Thank you.